Welcome to Privee, an architecture for automatically analyzing web privacy policies. My name is Sebastian Zimmeck. I'm a graduate student at Columbia University, and I'm presenting joint work with my advisor, Steve Bellovin. What is the problem? Not many web users read privacy policies. What is the solution? Automatic privacy policy analysis. We present Privee, a concept that takes privacy policies from websites, for example, the New York Times, Facebook, or Google, applies crowdsourcing as well as rule and machine learning classifiers, and returns the policy in a short, standardized, and convenient to read label format. In this talk, I will talk about the Privee concept as well as about our implementation in form of a Google Chrome extension. Particularly, I will motivate the problem, then discuss the concept, the performance and reliability of our analysis results, and conclude with a summary including future work. Let's start with the problem. Why should web users even care about privacy policies? The reason is that privacy policies implement the notice and choice principle. In the US and in many other countries, privacy policies are legally binding documents. They determine what a web service can do with the information that is submitted by users. Privacy policies are enforced by the Federal Trade Commission, and many of them qualify as contracts. However, only few web users read privacy policies. This leads to information asymmetry because users don't know what they're actually giving up or what they actually provide, market failure, and ultimately casts doubt on the notice and choice principle altogether. So far, 3 previous approaches were suggested. Most notably, the P3P project suggested a privacy policy language. That is a programming language that could be used by policy authors to express their policies, and these policies would then be interpreted by browsers and other user agents and notify users of privacy practices or alert users if the privacy practices conflict with their privacy preferences, for example. Another approach are labels, most notably No Privacy or Mozilla's Privacy Icons project. They try to replace long-winded natural language policy with short labels, for example, comparable to nutrition labels or drug facts. And most recently, the crowdsourcing approach gained popularity. Services such as Terms of Service Did Not Read or TOSBACK, they provide a forum for discussing policy terms, submitting analysis results, and making them available to the public. However, none of these approaches gained widespread acceptance, and this is both among users as well as among industry. Therefore, we propose Privee, and our Privee concept consists of 2 distinct components. First, we perform a crowdsourcing analysis. That means we access a crowdsourcing repository such as Terms of Service Did Not Read and look for privacy policy analysis results there. And if this repository or other repositories do not have the results available, we perform an automatic analysis based on machine learning and rule-based classification techniques. This concept fits into the existing privacy policy environment, as policy authors can continue to write their policies in natural language, and we can use labels as suggested, for example, in the Mozilla project, and the crowdsourcing repositories such as Terms of Service Did Not Read. Let's take a more detailed look at the implementation of our browser extension. The user requests a privacy policy analysis result. The web scraper obtains the URL of the website, in this case example.com, and also the policy text. The crowdsourcing preprocessor then determines, in this case, from Terms of Service Did Not Read, whether policy analysis results are available on this crowdsourcing repository. If results are available, they are returned in a label format to the user. If no results are available, our implementation performs a rule and machine learning based classification, possibly with a training cycle. The training cycle has to be done once. It happens initially when the classifier runs for the first time, and it takes about 30 seconds. Both the crowdsourcing as well as the machine learning and rule analysis take about 1 second. So that's the time it takes to return the analysis results to the user. Let's take a detailed look at the classifications that we do. We do binary classifications. So that means, for example, we look whether a privacy policy allows for the tracking of users for advertising purposes or not. We look whether the policy allows the collection of personal information or not. And this process is a 3-step process. First, a rule classifier tries to match a regular expression that is nearly always associated with a certain privacy practice. For example, in the example where we try to find whether a privacy policy allows ad tracking by means of tracking cookies or other tracking mechanisms, ad network is nearly always associated with this ad tracking practice. If such a phrase is found, the policy is classified as allowing ad tracking. If that is not the case, the machine learning preprocessor extracts text from the policy on which the machine learning classification will run later. We tried many different features, individual words, bigrams, longer phrases, but it turned out to be the case that bigrams are the most successful feature to use. This text that we extract from the policy is then submitted to the machine learning classifier, and the classifier that we use is a multinomial naive Bayes classifier. So surprisingly, this relatively simple classifier was as good as many other more complicated classifiers. And the classifier then performs the classification task. Finally, after the classification is done, a label is returned to the user. You can see on the left side what is displayed to the user, and we provide 6 different binary classifications. So this is not a summary of policy content, but rather in each policy we look for these 6 analysis points. The collection of personal information, profiling, for example, by obtaining data from data brokers and combining it with collected data, ad tracking by means of cookies, and so on and so forth. Based on this analysis, we assign the policy an overall grade, a letter grade, A, B, or C, so that the user gets an idea of the overall privacy level that the policy provides. The performance of our classification is shown in the table. Overall, we achieve an F1 score of 90%, and all of our classification tasks have an improvement in accuracy over the baseline, while the baseline consists of always selecting the classification that occurred the most for that particular category in our training set. And as you can see here, for these 3 elements, I only included 3, encryption and ad tracking have a much better performance than ad disclosure, for example. Why is that the case? We tried to find that out using binary logistic regression. We used the logistic function, and in our first model we focused on the policy overall. So we looked, is there anything with the overall policy that makes this result happen? And in our second model, we only focused on the extracted text per policy. So for example, we took in the second model the text length in words, and we tried to find out, is there a higher number of misclassifications for longer text or shorter text, for example? And what we found is that we obtain a statistical significance for semantic diversity. That means in case where we have a higher level of semantic diversity, we obtain more misclassifications of our software. Now, what is semantic diversity? Semantic diversity is a measure for the ambiguity of words. So, words with a high semantic diversity are more ambiguous than those with a lower semantic diversity. And you can see here the distribution of mean semantic diversity of our texts. And the example for a word with low semantic diversity would be, for example, encryption. The word encryption can be used in very few contexts only. But for example, words such as disclosure or collection have a much higher semantic diversity because they can be used in many different contexts. And what we found is that our software has problems with texts of high mean semantic diversity. How reliable is this result and our performance results in general? We needed ground truth. We needed a gold standard to determine that. So what we did before we ran our Privee extension is that we asked annotators, human annotators who are familiar with privacy law, to tell us whether a privacy policy allows collection of personal data, allows disclosure to advertisers, and so on and so forth. And the more agreement we would obtain on these analysis results, the better would be our yardstick to measure the performance of our extension. And you can see here 3 different types of measures: the absolute number of disagreement, the percentage agreement, and Krippendorff's alpha. Krippendorff's alpha is a measure that is used in natural language processing. It can range from -1, which means total disagreement, to 1, which means total agreement. And 0 would be a level of chance agreement. And as it turned out, the agreement on these individual tasks, encryption, ad tracking, and ad disclosure, is similar to the performance results of our extension. So encryption and ad tracking have fewer disagreements than ad disclosure. We applied another binary logistic regression model, in fact 2. And while our third model was not statistically significant, in our fourth model, we observed that the number of disagreements among the human annotators increased as the semantic diversity of sections, of policy sections, increased. So for example, the encryption section was mostly straightforward, while the disclosure section was much more prevalent to disagreements. Consequently, similar as in our performance, we observed that semantic diversity, an increase in semantic diversity, has an effect here in the sense that annotators have more disagreements. Now, this shows a linear regression, and it is no surprise, as performance and agreement correlate to the same variable, that the values of Krippendorff's alpha also correlate to the F1 scores. The question then becomes, does this result that policies are ambiguous impede the notice and choice principle? Because after all, one could argue that humans have difficulty understanding privacy policies, being notified of their privacy choices, and our results seem to say that computers, our algorithm, cannot help humans with that task either, as they are also confused by semantic diversity. Does that finding not militate against the notice and choice principle? And we believe that is not the case. And the reason is the following. For the majority of privacy policies in our test set that we investigated, we observed a statistically significant decrease of semantic diversity over time. So what you see here is the development of mean semantic diversity for semantics privacy policy. And if you look at the first version of their privacy policy, which stems from the year 1999, you see a mean semantic diversity of 2.1, and this value decreased until last year by approximately 0.35 points. We observed this for most of our privacy policies in our test set. Now, why is that the case? There could be two explanations. First of all, there's a natural conversion of language. Legal language often adheres to texts that were written before, and so text can become more clear. But also from a policy perspective, the Federal Trade Commission calls for an increase in standardization and making policies more clear. So this could be an effect that we see here. Now, what remains to be done? Mainly, the main point I think that can be taken from our work is that policies need to be made more clear. Analysis accuracy needs to be increased, for example, by exploring different features and algorithms. Crowd software interaction can be improved by, for example, using crowdsourcing analysis results as training examples for our automatic classification. And finally, usability should be investigated. For example, we can imagine something comparable to the little green HTTPS log displaying, for example, letter grades for privacy policies, things like that. Now, to summarize, we introduced Privee, a concept for analyzing privacy policies, and we think that our results are promising and that the automatic privacy policy analysis can be done, particularly that the ambiguity of language can be overcome, and as the policy ambiguity seems to decrease over time, we remain optimistic that this is a way for educating users about privacy and making privacy policies more understandable. Thank you very much for your attention. I'd like to now take questions. Thanks.
We have time for a couple questions. There are, I think, 2 mics where you can ask them. Please state your, are there any questions? Perfect. Yeah, please state your name and affiliation and favorite color. Oh, it looks like there's only one mic. I'm sorry for providing correct information.
Jaeyeon Jung, Microsoft Research, great work. Have you used your system to see whether a website that has just, privacy policy with this lawyer's term and then P3P to see whether their P3P expression indeed matches what you found from the sort of natural language representation of privacy policy?
Yeah, that's a great question, and we actually looked a little bit into that. We did not look at the matching because the problem is with many P3P policies that they actually don't match the natural language privacy policy. But what we did is we tried to match some of our analysis points to those of P3P. So in theory, what you can express in P3P can at least partly also be analyzed by our natural language analysis. But that's not a comprehensive analysis. We would need to look more into that.
Okay.
All right, if there are no other questions, let's give Sebastian another big round of applause while Matt sets up.